This video will give you a chance to learn about one of the ways that we can put stars on more even footing, so to speak, and give a number for their brightness that corrects for differing distances. You'll also learn to calculate this number when you know the apparent magnitude and distance for a star. When you look at this slide, you may recognize some constellations. What we're interested in, though, is to start doing some comparisons of stars. We want to compare the stars not by how bright they appear in a picture like this, but by using some sort of standard where we can take the differing distances to the stars out of the comparison. For the sake of this exercise, we'll just look at the stars in the asterism we use for the constellation of Lyra. First, though, let's go through some terminology. Some of this you'll already be familiar with. Asterism is a recognizable pattern of stars. The Big Dipper is probably one of the most famous asterisms. We use asterisms to identify the constellations we're looking at most of the time. The magnitude scale was introduced by ancient Greeks. Hipparchus, Ptolemy, and a poet named Manilius are each sometimes credited with developing the scale. We'll probably never know who actually did it. In their system, the brightest stars are first magnitude, and the dimmest visible stars are sixth magnitude. So as stars get dimmer, the magnitude number goes up toward more positive values. We've been using the term magnitude to refer to how bright a star appears in the night sky to our eyes. It's better to call that the apparent magnitude because it only gives us a number for how bright the star appears to be. We still use the same direction for the scale that the Greeks did, but the numbering is much more precise. Now, when we determine magnitude, we feed the light into a photocell and it'll give us a more precise number. We'll also find out, or we have also found out, that some stars actually have negative magnitudes. Here's a kind of representative number line here. You can think of the magnitude scale as something like a number line with negative numbers on the left, positive on the right. As you move toward the left from any point on the scale, you're going toward brighter objects. As you move toward the right from any point on this scale, you're going toward dimmer objects. Now we're going to consider a way to put all the stars on equal footing in some way. Apparent magnitude doesn't take into account the varying distances to the stars. We need another way to describe them, and the one we'll use first is called absolute magnitude. Somewhat arbitrarily, the absolute magnitude is chosen to be the brightness of a star if it is viewed from a distance of 10 parsecs, which happens to be 32.6 light years. The light year is a distance which light travels in 1 year. We've talked about this before. And the parsec is a unit of distance determined by the method we use to measure those distances. It's a distance for which the parallax angle is 1 second of arc. So these are the stars in the asterism we use for Lyra. I don't see a harp here, which is what it's supposed to represent, but there is a nice parallelogram. The brightest star in the constellation is Vega. Chiliac and Sulafat are named stars in Lyra. The other two stars in this asterism don't have such nice names, Zeta 1 and Delta 2. What are the apparent magnitudes of these stars? Well, Vega is a pretty bright star. That's essentially 0th magnitude, so that's brighter than a first magnitude star. Sulafat, 3.25, Chiliat, 3.50, so we've already moved quite a ways toward dimmer stars here, and it's actually difficult to see these things if you don't have dark skies. Delta 2 and Zeta 1 are really hard to see if you don't have dark skies. A lot of times the only thing you can find in Lyra is the star Vega. Now, the apparent magnitude is not a linear scale. Turns out that if you have a difference of 1, like from a 1 to a 2, there's a difference of about 2.5 times the energy carried by the light. So if each time you move up by 2.5 times, if each time you make a 1 magnitude change, you change by 2.5 times, it gets to be big differences pretty fast. The scale is actually worked out so that if you have a difference of 5 between two things, say from 1 to 6 or 0 to 5, there will be exactly 100 times as much light received from the brighter star. Now let's consider the distances to these stars. Vega is definitely the brightest star in apparent magnitude, but does it appear bright because it's an impressively large star or because it's close? Well, turns out Vega is somewhat close to us. 25 light years may not seem close when you think about what a light year is, but for stars it is, especially when you think it's 100,000 light years from one side of the Milky Way galaxy to the other. Zeta 1 is the next nearest star. It's a lot farther away than Vega. It's 156 light years away. And then we start getting bigger distances. Sulfat, 620 light years away. Delta 2, 736 light years. And Chiliac, 962 light years away. That's crazy far. When we see that star, we're seeing light that left it in the 1060s. That means the light had been traveling for 500 years before William Shakespeare was even born. And then it had another 460 years or so to travel before it reached us. So, which one of these is actually the brightest if we put them on equal footing? That's what we have to calculate. Some things that we'll use in our calculation are letters to stand for things. Capital M will be the absolute magnitude. A lowercase m will be the apparent magnitude. That's the magnitude we sense when we look at the star. And here is the formula for calculating this. A few things that may be a little bit new to you. Let's see, for one thing is a logarithm in there. Also, there's a variable I hadn't defined yet, d. That happens to be the distance to the star in light years. You could also do this calculation with parsecs. You do have to be careful to use the same units inside that logarithm parenthesis box. And so you'd have to use parsecs on top and on the bottom, but we're going to stick with light years for both. So let's calculate the absolute magnitude for Vega. Again, capital M is the absolute magnitude. That's what we'll be calculating. Lowercase m is the apparent magnitude, which for Vega is 0.03. And d is the distance, 25 light years. Here are the keystrokes we'd use. Imagine replacing the lowercase m with 0.03 and the d with 25.0. And on a TI-83, these are the keystrokes you'd do. They should be pretty similar on a TI-84 or a TI-30. Other calculators, I think you could probably figure out what you need to do. So coming down that left column in the table there, you can see what the keystrokes are, and then the right side is showing what the display on the calculator would be. The absolute magnitude of Vega is 0.61. Now, its apparent magnitude, 0.03, is brighter than that, and it makes sense. Its actual distance is 25 light years. If you imagine moving it out to 32.6 light years, it's going to get a bit dimmer. So the magnitude would go from 0.03 to 0.61. Let's check out the other stars in this constellation. Actually, first we're going to talk about logarithms a little bit in case you're unfamiliar with those. The logarithm of a number is an exponent, and it's the exponent that you would put on a 10 to get that number. This may be a little challenging to wrap your head around, but logarithms are exponents. We only calculate logarithms for positive numbers. There is a branch of mathematics that might deal with logarithms for negative numbers. It's called complex variables, but we're not going to do that. So that's something you might do in the year or two beyond calculus if you ever go that far in mathematics. Keep in mind, the logarithm is going to be the exponent you'd put on a 10. What exponent would you put on a 10 to get 100? Well, 100 is 10 times 10, or 10 to the second. And so that logarithm is going to be a 2. It's not usually this easy to figure these things out. Usually you have to use a calculator, but sometimes you can. And that's the logarithm because 10 to the 2 is 100. What exponent do you put on a 10? Well, you put a 1 up there because 10 to the 1 is equal to 10. What exponent do you put on a 1? You may have learned this in an algebra class. Any non-zero number to the 0 power is equal to 1. And so 10 to the 0 is equal to 1. How about 0.1? Well, if you follow the tendency, coming down the left column, we divide each number by 10 to get the next lower one. Coming down here, the logarithms each decrease by 1, and that tendency continues. The logarithm of 0.1 is -1, and that's because 10 to the minus 1 in our system is defined to be 1/10, which is 0.1. Now, what about a number like 60? It's not a 10. However, you can have exponents on 10 that are not integers. You may not have done that in a math class before, but that's what your calculator is good for. And it turns out if you punch those numbers in, or punch 60 into your calculator and take the logarithm of it, you would get 1.78. That makes sense. It's between 1 and 2, the logarithm is, and 60 is between 10 and 100, so you'd expect its logarithm to be between 1 and 2, and it is. You won't be doing anything like 60 in your head. That's what calculators are good for. Okay, let's figure out the rest of the stars in here. First, for zeta 1, we'd calculate it by punching in the magnitude for zeta 1, the apparent magnitude, and then put in the distance of 156 light years up there. I don't have the units in the parentheses anymore because it's light years on top and light years on the bottom, and they divide out. For zeta 1, with an apparent magnitude of 4.3 and that distance, its absolute magnitude is going to be 0.90. Think about this. With the actual spacing or actual distances to Vega and zeta 1, Vega is way brighter than zeta 1 happens to be. But if you move both of those stars to 32.6 light years away, they're pretty close together. 0.61 for Vega and 0.90 for zeta 1. That's not that far apart. You might actually have a little bit of a hard time telling which one is brighter if you had two stars that close together. If they're 0.3 apart, you can probably tell. Let's move on to Sulafat. So for Sulafat, magnitude of 3.25, distance of 620 light years. That's a lot farther away. Plug that into your calculator, and you would get minus 3.15, a negative absolute magnitude. Negative magnitudes are much brighter. We're moving to the left on that number line. That's way brighter. Sirius has a magnitude of minus 1, or yes, minus 1.09. Sulafat's going to be more than 6 times brighter than that. So that's a pretty darn bright star, or would be if it was at 32.6 light years away. Let's move on to Delta 2, 736 light years out. There's the calculation you'd punch into your calculator, which you can try for practice, and minus 2.57. Not as bright in absolute magnitude as Sulafat, but still pretty bright. Moving on to Chiliac, there are the numbers you can punch into your calculator for practice. and minus 3.85. So in absolute magnitude, Chiliac is the winner. The last three stars on the list share some pretty amazing numbers. They're all negative magnitudes, and they're all way brighter than the brightest star in the night sky, quite a bit brighter anyway. They're bright enough that if you were under a dark site and could see your shadow against a light background, any one of those three stars could cast a shadow that you would be able to see. The three of them, tightly bunched in that constellation of Lyra, would create a pretty impressive shadow. So that's something to think about. Also, each of those three is going to be bright enough to see in the daytime sky. You can see Venus in the daytime sky if you know exactly where to look. It's kind of hard to spot because it's just a point of light, but sometimes you can do it. Well, this would be a group of three stars close together that would each be individually possible to see. You might be able to see them easier, except that we can't move those stars. They're out at the distances they are. This is just a thought experiment that you might be able to do. You can see by looking at the absolute magnitudes that judging which stars are the most impressive is going to require a bit more than just looking at them. We'll have to do some calculations to be able to actually compare these things. And when we do that, we find out that Chiliac is by far the most impressive star in the constellation of Lyra. Vega doesn't look so impressive anymore.